So how about this, right? So we'll start with an introduction of all the pieces we have and why we chose them, and then dig into the measurements. Okay, so I want to start with the DUT, the device under test, right? So this is a GAN half bridge board. It's based on GAN product. It's a half bridge, and we have two of those circuits on top and the bottom. They're identical circuits. They're isolated from each other. The one on the top has MMCX connectors on it. The one on the bottom has square pins, so we can compare between those connectors and see the effects of those connectors, right? The reason we chose this is because half bridge is a building block for most of the converters people work on, right? So sync, buck, boost, inverters, right? And the challenges you'll face with this will be very similar to the challenges you'll be facing in most of these converters. Okay, all right. So that being said, let's go to the instruments we have picked, right? So we have our scope. I picked an MSO5 scope for this, and it's obvious it has 8 channels, right? But there are really 3 main reasons I picked this scope. The first one is the bandwidth, right? So I picked one that is 1 gigahertz, and the reason is think about the switches we are trying to measure and the transition times, right? So most of the GAN products in the market right now, from GAN systems, EPC, Transform, the turn-on times are usually in 10 nanoseconds or 5 nanoseconds, 6 nanoseconds range, and we'll see a very similar example here, right? And if you think about how much bandwidth, just with a very simple rule of thumb, how much bandwidth you actually need to measure that transition, that is the number you come up with, right? So bandwidth is one piece of it. The other piece of it is, think about the measurements we are trying to make, right? So we are trying to measure what's happening on VGS, right? We are trying to measure what's happening on the shunt. We are trying to measure the gate charge and so on in presence of a VDS measurement, which is 400 to 600 volts, right? So if you think about this problem, the vertical resolution you need has to be really high if you really want to see details on this, right? I'll give you another example. Think about conduction losses, right, or switching losses, and think about the RDS on measurement, which is another hot one. The RDS on measurement is in conduction area, which is really small, usually in millivolts, depending on your RDS on, and you're looking at it in presence of a VDS measurement that can be 400 or 600 volts, right? So you really need the vertical resolution, the number of bits to resolve that to get decent accuracy from that measurement, right? So 12 bits is the second reason, and the third reason is sheer number of channels, right? So we all know when we start solving problems and we are stuck, we want to see as many signals as possible, right? So the more I use it, the more this has become my favorite scope, just because the sheer number of channels, and I can see a lot of things at the same time, right? So those are the main 3 reasons I chose this scope, and I, apart from it's cool, right? But that is one of the, the main reasons, right? Now, thinking about these measurements, I think one of the key, probes you need for this measurements are this ISOView probes. These are isolated differential probes. What that means is it has an optical isolation. There is no electrical connection between the probe heads and the scope, which gives you a very, very high common mode rejection, right? Why do you need it? So half bridge, right? So you're talking about half bridge, you have the ground level signals, all good. You can do that with passive probes usually, right? But the high side, you're switching really fast and you need a differential measurement, right? So you need to reject all the common mode you can at a very, very high bandwidth, right? That's where this comes in. So these probes are rated for 1 gigahertz and 800 megahertz respectively, 2500 volts for silicon carbide designs, and then 50 volts for smaller GAN products, right? So if you're trying to measure gate measurements or shunt measurements, TIVM is the product for you, and then for higher voltages you usually use a TIVH, right? So those are the probes, and last but not the least, we'll use the TPP 1000. So these are the passive probes. We all know this is a standard probe, and one of the challenges is obviously the ground loop, right? So as soon as you have this ground loop, there's not much you can do with this measurement, right? So this has to go. This is a no-go. It cannot work, right? So a lot of ways people solve this challenge is by using those spring connectors, and you essentially go on the sleeve, take the sleeve off and put the spring connectors on top of this, right? That's good. It solves some of the problems, but you still have pickup problems because you still have that small ground loop as well as ways the signal can inject into it, right? And we are getting a lot of issues with with this connector problem with this circuit, and that's why we came up with a solution for this, right? So this is pretty cool, right? So what we did was we created an adapter. This is an MMCX adapter for the TPP, standard TPP 1000 probes, and you essentially plug it in and you have this beautiful high frequency connector. So once you have these connectors, you can essentially just plug it in and there you have it. In summary, this is pretty much all the instruments we have for this measurements. We'll bring in some more stuff as we go through the sessions, but let's get rolling and look at the measurements.